So what we're going to do now is we're going to look at one more tab of the spreadsheet. Actually, this will be the last tab of the last spreadsheet we look at in one of our videos. It's kind of heavy. Huh. Anyway, combine samples. I'm going to click over here, and it's going to look a little bit overwhelming at first, but let's work through it. What I've done in this spreadsheet, I'm going to break it down into a couple different regions here. Let's look at the graph first. Now, the graph down here is actually 5 graphs in one. Each of the graphs you see right there is exactly the same graph you saw back here in the 4, 9, 16, 25, and 100 sample sizes. You see them here too. I changed the graphs to make them look more smooth, more like bell curves. Because since we're seeing that kind of distribution, we're seeing the idea of a normal distribution, I figured let's make it look like it. That's funny, that second one back there looks kind of like broken top. One of my absolute favorite ways to spend a summer day. And if I re-randomize, you can see that those graphs change just like they did before. They definitely kind of undulate, but as the sample gets larger back there towards that 100 sample size, there's not a whole lot of undulation going on. As a matter of fact, if you look at the raw data, most of the data is showing up only in 4 categories back there. Now, let's leave the graphs alone for a second and let's look up to the top part of the spreadsheet. Now, the top part of the spreadsheet, you've got the average and the standard deviation from the population. We never know those, but as statisticians, we want to know those. Okay, so I'm going to keep those there just for reference. What I want you to focus on now is the sample size column in column E there, 4, 9, 16, 25, and 100. The average of the X bars. So what this is, I took all 1,000 samples in each of the 5 sheets. Boop, 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 boop. I went into each one of these things, located all the sample averages, they're over here, and then took the average of all of those. And that's what you see over here. And what I want you to look at that column F right there for sample size 4, 9, 16, 25, and 100. Check this out. Check that out. No matter what the size of the sample is, no matter what, whether it's 4, whether it's 100, whether it would be 10,000, I mentioned before I tried to make a sample size at 10,000. It doesn't matter, because 10,000 would not get you any better an estimate for the average than a sample size of 4. They're all hovering right around that 8.17. So why would you ever draw a larger sample? Well, that's where the next column comes in handy. And also the graphs, if you're looking at the graphs. The next column is the standard error around the mean. Column F gives us what's known as accuracy. That means, on average, we're targeting the average we're looking for. I know it's kind of weird to say that, but it's true. On average, the samples are targeting mu, the population average. So the sample average is a really, really good estimate for the population average. Now here's the catch though. The smaller the sample, the more variability your sample average is going to have, which means it runs the risk of being further away from average. Aha! So that's where the standard error comes in. Remember what this is? It's the standard deviation of the sample averages. So take a look. When you sample 4, the standard errors looks like they're hovering around maybe 1.32, 1.33, somewhere in that neighborhood. They're bouncing around quite a bit, but they're definitely focused on a number like 1.33. That's actually a pretty good place to stop. When the sample size is 9, looks like it's around 0.89, maybe 0.9, somewhere in that general area. When the sample size is 16, looks like it's hovering around, I don't know, maybe 0.7, 0.6, something like that. It's 0.65, somewhere in that neighborhood. When the sample size is 25, looks like it's 0.51, 0.52, somewhere in that neighborhood. And when it's 100, it looks like it's about 0.2, I don't know, 0.27 maybe. Now here's one of my favorite parts of this class, and it's kind of fun that it's at the very end of our time together. These numbers in column G are actually related to this value of the population standard deviation, which of course you don't know. But check out what we do know. Let's look at how these standard errors are related to that little sigma over there. So you notice they're all smaller, right? They're all smaller. So let's ask a question. How many standard errors in one little sigma? Actually, you know what? This is dumb. I could insert, I think, I could insert the symbol for little sigma here. How many standard errors in one little sigma? Let's insert that and close it. Okay, there we go. And it's a question, so let's make it a question mark. There we go. How many standard errors in one little sigma? So I'm going to take the sigma, the 2.69, and I'm going to divide it by each of these standard errors. And I'm going to drag that down. Now, those numbers are not perfect. All right, those numbers are not perfect. They're not, oops, they're close to those values right there, but they're hovering very closely to these values. And if I hold down the randomizer, you can see that, right? I mean, they're changing right now. I'm holding F9 down. You can see the spreadsheet is changing, and you saw that bottom one just flipped over to 11 and then flipped back to 10. But they are basically 2, 3, 4, 5, and 10. Now, I want you to look at those numbers, 2, 3, 4, 5, and 10. Do you see how those numbers are related to the sample sizes of 4, 9, 16, 25, and 100? If you do, great. If not, let's go to the next video and figure it out.